Okay, here's a video of how to solve a buffer problem, a buffer that's been insulted with some strong acid. So the question is, what would be the pH of a 1 liter 0.1 molar glycine buffer at pH 10 after the addition of 10 mils of a 1 molar strong acid solution? So this is definitely a buffer problem. It says the word buffer, and so I'm going to immediately write down Henderson-Hasselbalch equation. And what I'm going to try to do on this problem is find out what I know and what I don't know. Now, it's weird. Do I know the pH or do I not know the pH? Well, it seems like there's two buffers here in play. There's the original buffer, and then the new buffer that happens after I add the strong acid insult to it. And so I know the original pH of the uninsulted buffer. I don't know the pH of the buffer after the acid. So I think what I'm going to do is try to just describe the original buffer as best I can using Henderson-Hasselbalch, and then see how it's going to change after I add the acid. So the original buffer has a pH of 10. I know it's pKa. It's given to me and it's a constant. I do not know the concentration of the base or the concentration of the acid. And this seems like it's going to be a problem. I've got one equation here and two unknowns. There's no way I can solve for both of those unknowns mathematically unless I have another equation. So to find another equation, I kind of look at my question and say, what other information has been given to me? Well, I'm told about the volume and the concentration of the strong acid, but that's not really relevant to my original buffer. I need to figure this guy out first. Well, I'm told I've got 1 liter of a buffer, and it's a 0.1 molar glycine buffer. Now, when we describe the concentration of a buffer, we're not just describing the concentration of the acid or the base. We're really describing the concentration of both of them together, since they can convert back and forth as they act as a buffer. So this piece of information seems pretty relevant, and actually it's the source of my second equation. Well, if I have a 0.1 molar buffer, that means that the concentration of acid plus the concentration of base is equal to 0.1 molar. Now I have two equations with the two same unknowns. I can substitute in something for base or acid. So let's choose one of those. So the concentration of base is going to be equal to 0.1 molar minus the concentration of acid. I can plug that in right there and end up with a new equation. That only has one unknown in it. So let's just do some algebra and try to solve for the concentration of acid. Then I can solve for the concentration of base, and that should give me a complete description of the original buffer using Henderson-Hasselbalch. And then maybe I can figure out what to do with it after adding acid. So let's work through this. Let's move this 9.8, combine it with the 10. So 0.2 equals the log of all this stuff. How do I get rid of the log? I take both sides to the 10, inverse log of both sides, and that will get rid of the log. I said 10, let me do this, to the or 0.2 is what I want to do. 0.2 inverse log is what? I guess on this thing I have to do inverse log 0.2. There we go. 1.2 0.58 equals 0.1 molar minus concentration of acid over concentration of acid. I can cross multiply, right? 1.58 times concentration of acid equals 0.1 molar minus concentration of acid. I can move these acids to the same side. This is minus 1 times concentration of acid. So if I move it to the other side, I would end up with 2.58 times concentration of acid equals 0.1 molar, and the concentration of acid equals 0.1 divided by 2.58 equals 0.0388 molar of acid. Okay, does that make sense? Well, let's plug that back into our equation here, and what we would find is that means the concentration of base is going to be equal to like 0.0612 molar. Okay, now I'm going to step back. Does this make sense? Well, I've got a buffer here. The acid plus the base equals 0.1 molar. That's good. And it has more base than it does acid. Does that make sense? Well, I know my buffer pKa is 9.8. I want that buffer to be higher at pH 10, so I better have more base than I do acid, so I can bring that pKa up to a pH of 10 through this ratio. So this seems pretty good. And really, I've described the original buffer pretty well. I know its pH, I know the concentration of both the acid and its conjugate base, I know the pKa, I've got it all good there. So let's see what happens after we add our acid. Well, in this case, my lights, the pH is not known, right? That's really the entire question there. The pKa is still known, it's a constant. I do not know the concentration of base and acid, but I know what they start with, right? We started at 0.0602 molar of base and 0.0388 molar of acid, and I know that these things are going to change by a certain amount. So if I add a strong acid to my buffer, then my conjugate base is going to jump on it and convert it to the weak acid. So for every molecule of strong acid I add, I'm going to lose that same molecule of base, and it's going to convert it to a molecule of acid. And so my ratio is going to change by this factor X. Now what is X? Well, it depends on how much acid I'm adding. I'm adding 10 milliliters of a 1 molar strong acid, and so we're adding 0.01 liters times 1 mole per liter. We're going to be adding 0.01 moles of acid. Okay. Now, I have a problem here because my concentrations here are in moles per liter. I can figure out the number of moles of acid, and I could really figure out the total volume at the end, but you don't really have to worry about it. Since this is a ratio, I can really just get rid of these molar and just treat them as a number of moles. And the reason why is because any amount of liters that I have here is just going to cancel out as part of this ratio. So I like to just have the number of moles here. So I'm going to substitute X for 0.01 moles. I'm going to subtract that from the top, and I'm going to add it to the bottom. So my pH is going to be equal to 9.8 plus the log of 0.0512 over 0.0488. Okay. Now, let's do that on the calculator and see what that ratio is. My ratio is evening out, so I'd imagine my pH is going to get closer to the pKa here. So 0.0512 divided by 0.0488 equals 1.049. So I have 9.8. Let's take the log of this. Point 0.0208. So 9.8 plus 0.0208. .82 is my new pH. Does that make any sense? Well, my original buffer was at pH at 10. I added some acid and it decreased the pH to 9.82. So I'm going in the right direction. It didn't make a huge jump, which really reflects the buffering capacity of this. If we added this concentration of strong acid to water, we would end up about with a pH of 2. So this is a decent buffer, and it did a decent job of maintaining the pH.